Hi everyone, thanks for joining me on this research seminar. So for today the topic is the quest for AI systems, and AI obviously stands for artificial intelligence. So what I want to cover today is a number of different topics because quite often AI is seen as very broad, and so I'm going to zoom in on some of the challenges that we're facing in the AI world. But also, why would we try to build an artificial brain? And there's a raft of reasons why we need to improve on existing technologies. We're then going to have a look at how our current and existing computing platforms perform with regards to the tasks that we're trying to achieve from AI, but also how this compares with the human brain and how these two are actually two sides of a completely different coin. So how we can improve our technology moving forward means that we're going to have to look at new platforms and develop those. And these new platforms are very likely to take inspiration from the human brain, and so there's a lot of work in this context happening around neural networks. And I will be touching on that very shortly because the majority of what we actually do is based on a functional understanding of the brain, and there's a number of theories out there in that context, and that is what we will cover. And we will then move on to a number of elements of work that have been happening in that area as into how we are effectively trying to build an artificial brain. We're going to end with something which I call the sound of music, which is based on a technology that we've been using or trying to explore further for our development of the brain, and which is actually demonstrated to be particularly useful for other areas as well. In this case, we were looking at audio as a demonstrator for our technology, and this is where we've already seen some potential benefits, and I'm going to demonstrate that to you as well. But first off, what are the benefits and challenges for AI? And I'm going to start off with something that's again been hitting the media for quite a number of years now, which is called the Big Data Challenge, where I'm going to throw some numbers at you, which aren't as many as you would see with normal data. But what is big data? It's effectively a broad term for data sets so large and complex that traditional data processing applications are inadequate. And if you think about it, the definition already inherently states that our existing approaches are probably not sufficiently ready for these large data sets. It's come into the media, possibly not always in the positive light, because of things like Facebook and Google, who are collecting a lot of usage data and then are using that to try and give us so-called targeted advertising and things like that. But there are potential benefits of this as well. And so if you look in the medical world, which is where one of these benefits lies, a doctor spends a lot of his time learning for their degree, but keeping up to date and knowing everything that's happening in the medical world is nearly impossible these days, considering the amount of publications that are coming out on a very regular basis. And so if there are specific cases where a patient has, for example, a specific gene mutation, then it may be very interesting for that doctor to know that particular medicines are not going to be as effective as others, as studies may show at some point around the world. And so if the doctor was to enter his diagnosis into the system, and the system then looks at the whole picture of that patient and combines that, it may say to the doctor, have you heard about this study? Are you sure you're going to prescribe him this medicine rather than that medicine? Because this study actually shows that the second medicine is going to be way more effective in this case. And so this is where there's potential benefits on this. Obviously, there are companies like IBM who've been looking into this, and we can have lengthy conversations around some of the ethical and even legal implications of some of these areas, but that's not really what we're here to do today. So what I really want to do is I want to kind of give a very quick overview, true means of an example of how big this big data challenge is, but then also how challenging it is to solve that using automation, which is what we'll see in a second. So if we're looking at YouTube for quite a number of years now, it is known that there is about 300 hours of video uploaded every minute. And calculating that at about 1 gigabyte per hour, that means that we come to about 432 terabytes of data per day. That's quite a substantial number. Now, this is actually only a very minor fraction of the 3 exabyte of data that is produced per day. Now, over a year, this leads to about 1 zettabyte, which is 10 to the power of 21, and 1 zettabyte equals about 250 billion 2-hour HD movies. Now, if you think about it, that's a substantial amount of movies. And I know some people have been trying really hard during lockdown to spend an amount of time watching all of this video content, but 250 billion hours is massive. I don't think anyone's going to succeed on that very soon. So if we're now trying to look at how to analyze this data, so you've got about 300 hours of video uploaded per minute, so that's 432,000 hours per day. Now, if you were to employ people to watch videos for 8 hours a day, you'd need a team of about 54,000 people. That's a quite substantially large company. That's about the size of Google today. So if you then consider that YouTube is about only 0.00014% of all the data generated on a daily basis, then if you were to say we want to analyze all of the data that we humans are currently creating, we would need 38 billion employees to just look at this data. We haven't even analyzed it, categorized it, or done much useful with it. We haven't even, in my calculations, considered sick leave, annual leave, lunch breaks, and all the other things that normally come with employment. But you can understand, if we need 38 billion employees to deal with this, we can easily, obviously, solve unemployment issues even after lockdown. But getting to these 38 billion people also means we are going to be creating much more information. And so, is this information useful? Is it actually one of the very first questions that we often need to wonder? And so these days it's much cheaper to just store the information and then see whether it ever gets reused or not, rather than do anything else with it. Now, if we were to try and automate this, and I just want to highlight one of the perspectives of automating this, if we consider the human brain as it stands, depending on the source you're looking at, the human brain is considered to use around 20 watts of power. If you were to use comparative conventional computing, so as we have it on the market today, we would require anywhere from hundreds of megawatts to about a gigawatt to achieve the same kind of functionality. And the machine, it wouldn't be a simple machine, would require the size of a football field. Now, I want to put this in perspective with the largest power stations on this planet. And as you can see on this table here, the actual largest one is the Three Gorges Dam in China, which has a capacity of 22.5 gigawatt, runs normally around half of that capacity. It's a hydropower station. And so based on whether we're going for these few hundreds of megawatts or a gigawatt, we're anywhere from tens to several hundreds of possible equivalent humans, as I call them. Second biggest power plant is in Brazil. It's an hydro station running around the same capacity, so same number of equivalent humans. Then we skip a few to come to the largest nuclear power station, which is in Japan, which produces around 7 gigawatts. And so again, we're looking at 200 to 300 equivalent humans maximum. Now, if you were to add up this right column, you can see you're nowhere close to achieving the 54,000 to deal with the YouTube challenge, let alone starting to deal with some of the other challenges of all the other data that we're creating. So the problem as such that we have is really big. Now, this is just one aspect of it. There's a large number of other aspects, because people will say, well, AI, we've already got some technologies out there, like image recognition, like object recognition, And one that's really been hitting the homes over the last few years is speech recognition. And so what are we trying to achieve is we're trying to improve the recognition accuracy. A lot of these technologies, if you look at speech recognition, etc., they will be in the 90s plus. Now, if you think about a normal phone number, normally you can go up to about 10 digits. If you have a recognition accuracy of 90%, then that means that you're very likely to still get one of the numbers out of your whole telephone number incorrect. And that kind of makes the technology as such useless. Because, you're always going to be dialing a wrong number. You're never going to get it right straight away. Now, the other thing we're trying to achieve, obviously, is quicker response times, trying to create smaller devices which are not necessarily requiring connection to the cloud, because a lot of our technologies now are making use of the cloud, very much because we have that additional performance, as in processing performance, available in that setting. And if you obviously want to go mobile, you want to do this with very low energy requirements. Now, if we just look at image and object recognition, again, one of the things that often happens is if you start to partially occlude the object, so you have a tree in front of a house, you may not even recognize the house as you normally would. So there's a whole bunch of challenges there that we are facing in technology, and our recognition accuracies over the last number of years has actually increased with very small steps, not really achieving what we as humans as such do. Now, where does this come from? Now, I want to take a small detour into looking at our current computing platforms. And to do that, I want to start with a very quick analogy. I'm not going to go into too much detail on this, don't worry. So, digital technology, as we know, is very much based on, the binary digit. It's either a 0 or it's a 1. And in this case, I've linked this with being either a white car or a black car. But then, to represent any data properly, we need loads of these cars, and I really mean loads. Because if you consider it, if you either have a 0 or 1, the only thing you can do is say yes or no. So imagine I was to do this presentation by just saying yes and no's to you, and the sequence and order of my yes and no's would then lead to a particular meaning to you. Now, from a perspective of efficiency and data representation, you can imagine that my presentation is probably going to take way longer than if I can use the variety of different words that I can use today. And so the quest here is, if we are trying to achieve human brain intelligence, do we need to think about data representation? And we'll come back to that a bit later. Now, digital technology as such, going back in history, was actually developed to communicate over noisy channels. So if you're communicating over a long distance channel, it's very useful if you can just say yes or no, rather than all of the shades of grey possibly that you may otherwise have, because if you lose a bit of the grey along the line, you're actually lost. And therefore, if we look at how it's been developed and where it comes from, it is brilliant at doing things for which we've been using it a lot, which is arithmetic operations, logic operations. But does it achieve what we require for a human brain functionality? And so let's have a look at how some of this compares, how some of our conventional computing compares with what the actual human brain does. If we start off with this arithmetic and logic functionality, then a conventional computer is basically born to do that. Now, I'm yet to learn and meet the first baby who's actually born with the arithmetic and logic functionality. It is something people go to school for, right? We don't come with these skills onto the planet, and so it seems unnatural to us that our brain would be working in that manner at the lowest levels. Now, if we're looking at the actual operation, then again, conventional computing is very deterministic. It is all about getting the right result, and getting that as quickly as possible. Whereas if we look at the human brain, we may say, well, we normally get to the right result, but there's probably some kind of stages in between that make it not as perfect along the way. Yeah, and so we come back to this as well a bit later. When we're looking at data and storage, then conventional computing, we're building up very large databases, we're storing these on hard drives, and we're using very specific addressing or a numbered address to actually access this data item. But if we're looking at the human brain, we very much get an idea that the data itself is central to everything that's happening. And the data is stored in association with other data. And again, one of the points that we're going to come back to in more detail later on. So when looking at data density, which is an item I covered already, for conventional computing, this is very low because of your 0-1 representation. If we're looking at anything around us as in nature, this is often way higher to an extremely high standard. Yeah. Now, the basic components that are building up or this system as such, in conventional computing, we've got processors, memory, and communication, 3 different parts with very specific different functionalities. Whereas when it comes to the human brain, we've got neurons, and there are different types of neurons, but they all kind of work in the same way. The differences in the neurons normally lies in how the synapses are connected, and so whether they go more horizontally or vertically in their extension. And so what can conclude overall for conventional computing, if you're looking at the actual hardware elements, the flexibility is really limited. So the flexibility really comes from all the software that we run on top of that hardware. And when it comes to the human brain, we are massively resilient. So just look at the current COVID-19 situation and how we humans have had to adapt to that in a very short time frame from so many different perspectives, and we've managed that in most cases very well. So another quite quick look at how the current trend on computing has been, and this covers a quite extensive period, so all the way from the 1970s to 2015, and actually if you'd look at 2015 all the way to now, there isn't going to be that much change. So we can see on the red line at the top that the number of transistors is increasing significantly, and that is clearly Moore's law. And we will continue to support that for at least the very near future. There's been many predictions that this is going to end, but one is still to see as to when that exactly is going to happen. Single-threaded performance, so that is one task being executed on the processor as such. You can see that this actually as a performance is starting to kind of flatten off as such. Similarly, we can see that for most of the other curves. So the frequency, so our computers, if you go back 20, 30 years, we used to buy a new computer every 3-4 years because the processor was so much faster than the previous generation. For the last few decades, that's no longer the case. And so you can see that this is flattening off quite nicely. At the point where this flattens off, you can actually go down and see that the marketing then started to play in on how many cores they were selling us, and that was the new marketing tool to get us to buy new equipment. But again, you can see that that is starting to flatten off, and you can also see that from around 2000 onwards there's been a lot of effort with regards to power consumption and reducing that, and that comes down to us moving into more and more use of mobile platforms, where this is obviously of significant importance. Now, one of the things we need to be conscious of is with regards to designing any computing technology. That is that the way data is represented, and we can take an example here as being binary, and the way it is being processed as into arithmetic and logic functionality have a very tight relationship also with how it's being implemented. And so what we had to conclude is that as soon as you start to say, I want to change one of these three, you actually have to change the other ones as well. And so you can't simply take one of them and change them. So if I'm not happy with the data representation, I will have to change some of the other elements as well. One side note here as well is I'm talking about digital computing in general, and that is being implemented in microprocessing. It's also being implemented in a lot of work around the optical and quantum computing area, which are basically based on the same digital principles being extended into what you can call a different technology. But the actual basic principles that underlie these are not changing. And that is very important to take into account. So when people start to look at optical and quantum and say this is very promising, it is going to be more powerful from the perspective that the technology is slightly more powerful, but it is not going to overcome some of the challenges that we're facing with digital technology when it comes to achieving artificial intelligence, and that's very important in this context. So a quick jump into the neural networks perspective, because we want to look at how the human brain deals with things. And so a lot of research has gone into mimicking the neural networks that are forming the basis to our human brain as such. Now, some of the challenges that we've got is obviously how do we mimic these? How much of the neural networks that are in our brain do we actually understand to sufficiently mimic them? And so if we look at the top of this slide here, we see a number of neurons. We see a number of neurons with their main core here in the middle, and then a whole bunch of synapses. And as you can see, these then often lead to what we call the firing or the spiking model. And a lot of these spiking models actually are brought back to the very simple, the bottom line is a 0 and the top line is a 1. So we're back in our digital perspective. But if you look at the very detail of these spikes, you will see that a lot of these spikes are different. So there's so many different types of spikes. And if you consider that biology has had so many years of improvement, it would seem unfair to assume that these spikes are all meaning the same, even though their shapes are different. But that is what underlines a lot of research in the neural network context. Additionally, we often only look at the electrical or electronic element of these spikes, and we're not looking at the context of the chemicals and all the other elements that come into play. Yeah. So what we need to be conscious of is that we're actually looking at a very small, very limited perspective of our understanding, and our understanding itself is also very limited of what is happening probably in the human brain itself. So is this going to be a valid platform to build on? I think we can learn a lot from trying to do that, but we may not necessarily get to creating a human brain in this manner very quickly. But let's see. I support people doing this. This is probably not the route that we're going to follow anytime soon. So these artificial neural networks are often run on our existing digital platforms. And again, one has to consider that another limitation is you just have limited interconnectivity. So I now have taken a three-dimensional interconnected structure like the human brain, and I've basically mapped it onto a 2D chip. And so you have limitations in what you can achieve. Yeah. Now, needless to say, actually, we have done very well with some of this technology, and we've got applications out there that work quite well. We are working on things like neuromorphic chips. Some of those are not even digital anymore. But again, some of these also struggle with flexibility, etc. And so there is work out there which I'm sure is going to be leading to more interesting applications moving forward. Now, this is not the route we follow. So what is the route we follow? We actually look at the brain from a functional perspective. And quite often people say, if you look at the brain from a functional perspective, where's your information? If you look around to what's been published, there is a number of models out there, and I've mentioned a few here. The first one is actually one of the ones that has probably been with me for the longest, is hierarchical temporal memory, in some cases referred to as HTM, is developed by a company, Numenta, in the US, which is led by Jeff Hawkins, also the author of a book on intelligence. And if you're interested in this topic, I really recommend that as a very first read in this area. As a company, they've also had commercial routes that they wanted to explore, especially to keep themselves going, even though they do have a very strong research focus. And so some of their technology has been spun into the use for predicting stock price changes. And that seems to be working quite well because they've been doing this for a number of years now. Another model is the SB theory, and the SB theory stands for simplicity and power, and it has more of a biological background. So it is based on multiple alignment found in bioinformatics. And if you start looking at DNA sequencing, it is how these DNA sequences actually match and align with one another. And that's the underlying principle to do this model, or as a large one at least. As a last one on this slide, associative memory. Again, we've mentioned this in the past, and I'm going to come back to that in a second to you as well. There's other models out there, but if you look across all of these models, there's a number of things which are common. And the common things is actually something that is very, appreciative by most of us humans, because that's what we see in daily life. And so what we see is that we learn through either repetition or through experience. And repetition is your typical studying. You do it over and over, and you do exercises until you get it. Yeah. Experience is quite often the very quick and snappy things. You put your hand on a warm surface, you quickly learn that that's not the right thing to do, and you're going to be very cautious of doing that the next time. At least I hope. So. But the other thing we're also very good at is we're very good at recognizing patterns, and recognizing patterns as well in space as well as in time. And so a lot of these models that I've just mentioned, like hierarchical temporal memory, have that time dimension to them. Whereas if you look at a lot of other research out there, a lot of the pattern recognition often restricts itself to space as such. And with space, I then also mean looking at that image, how do you recognize an object in that larger context? So that is what we need to consider as space. So coming back to something I've mentioned a few times by now, associative memory. So the human brain can be seen as a large associative memory. What does that mean? It means that we're actually storing all the information in association with other information. And so if I was up to ask you now, what did you do last Friday 4 p.m? and most of you would struggle to come up with an answer. You would probably start by asking questions as in, can I have a look at my agenda? And what you would then do is you would start to derive from your agenda what you may possibly have been doing. And mind my words, what you have possibly been doing. So it's that uncertainty element is in there, trying to get to that certainty, which is what I talked about earlier. Now, if I was to ask you, what did you do the last time you went to the beach? Then you're very likely to start telling me a story about what you did, whether you had ice cream, whether you took the dog along, played some ball games, etc., etc. And for most of us, going back to the beach is probably much longer ago than last Friday. So you have that going to the beach as an item of information, and then a whole set of associated information, which is what builds up your story. So what we tried a number of years ago is actually see whether we can build up some of these associative memories. And rather doing it in a digital way, like many of people out there do, we tried to build an analog one. And we also tried to make use of something called a memristor. Now, a memristor, if you look at the top right of the slide, is actually the fourth passive element in electronics. And so most people have heard of resistor, capacitor, inductor, and a memristor actually gives you a relationship where the resistive value of your element can be changed, but then it stays at that particular value until you change it again. Now, if you look at the different ways of storing these values, which is what we find here in the middle, we've actually created two cell types. And normally what people do is they create some kind of bridge structure, as you see there on the slide. And because these elements, these memristos, have a polarity to them, the difference between cell type 1 and cell type 2 lies in the middle elements having their polarity changed over. And that's the only difference. Now, what we then did was we actually, because we built these cells, you can see the green probes and the red probes, and that means that we actually could measure at 2 points, and so we could actually store two values in these cells, and that was important to us because we wanted to demonstrate that you could do more than one storage, and you could do it quite well as well. So if we now go to the bottom of the slide, you can see that we've got a particular input vector, and then to the right, we've got a number of stored values. Stored values. And so what we're trying to do is we're trying to find these inputs and see how this matches with the existing values. And hopefully we would find the closest match, because that's really important. In an association manner, you are trying to find what is closest to what you're looking for. And if that's perfect hit, that's perfect. If that's not perfect hit, you are still trying to find the closest. If you can't find anything, you basically say, I don't know, right? So we managed to retrieve, in this particular case, the 0.22 and the 0.35 values, which was what previously stored and is closest to the actual input. Now, most people say, well, if you do analog processing, then you're not very tolerant to noise. And so we basically threw noise at the system in a variety of different manners. And you can see at the right bottom here that if you start to throw noise at it, which is what you see as the horizontal blue at the bottom, you can still retrieve the actual values, or at least the closest match. And that is because if you are searching for the closest match, noise is no longer that as important as it would be when you compare that with a fully deterministic system, which is what our digital platforms are. And so what we did in addition was we actually then also compared the noisy situation for the different cell types, cell 1 and cell 2. And if you look at the cell type 1, which is the left-hand graph here, you can see there's quite a bit of noise coming in here, but we still retrieve the correct values. On the right-hand side, cell type 2 is storing some of the values in the opposite manner, which actually brings a benefit if you look at it from a noisy perspective. Now, one of the conclusions we had to make with this approach was identifying, the right cell was one thing. So if you have multiple stored values, you can easily identify that one element, but then we needed a lot of high-spec electronics after that to actually identify the one that was the closest match. And producing that in everyday commercial settings would be really challenging to still achieve that because of the high spec requirements after our initial cell values. And so we kind of left that parked, and then we moved on to some further approaches, or new approaches. So just as a summary of some of the things I've already said, so one of the things we highly focus on is finding similarity and finding closest matches. Now along that spectrum you've got an exact hit all the way to nearly the exact opposite, which is your differences. Yeah? And so this is the spectrum that we're looking at, and this is the spectrum we want to get to very quickly. And if you plan on doing this with a digital computer, you effectively need to make loads of distance calculations between your input and all of your available stored values, and that takes a lot of time. Whereas what we're interested in is the higher spectrum, the spectrum where we've got that similarity or that difference. All the middle is an irrelevant time waster effectively, and so we don't want to spend time on that. So differences as such are very important to the brain because this is how we remember phone numbers. And it also helps us to reduce data storage requirements. So what you see here is a graph where we've applied principal component analysis, grouping this into 3 different groups, and we use that in front of a standard typical machine learning algorithm. as you can see it here. This actually demonstrated to us that we can save a substantial amount of data, and that only 16% of data is unique, and actually also doing then the similarity detection, so in using this tool to find the right results afterwards, we had an improvement from around the 50s to around the 80% mark, which is quite substantial. So what are we doing? We're actually aiming towards the similarity and identifying the similarity very quickly. We're currently using standard physical principles to do that. I can't go into the details of that because it is still highly sensitive at this point in time. And while we've got a basic cell to do that, we are now trying to take this forward to recognize patterns in space and time. We are currently doing this in a variety of different means, and so one approach is using electronics, the other one is using optical technology, and we are very confident that we can easily map this onto quantum implementations without actually suffering from the current restrictions that quantum now suffers from, like all of the thermal rundown, etc., etc. And so if we can take our basic cell and start to recognize these patterns in space and time in the bigger picture, then we may be on for a quite interesting move on in technology here. So how does this bring us to the sound of music? Well, one of the things we were doing was actually using our technology to and using audio examples to demonstrate our technology and see how we can find matching information, but also how we can, in this case, it was recognizing instruments. And so when we started to decompose our instrument, our sound sample, and using existing technologies like FFT, fast Fourier transform, or a more advanced approach, constant Q transform, we actually found that our approach was slightly better, and that was because each of these, FFT as well as constant Q transform, they have an averaging principle within them. Because you take samples together, you window them, depending on the size of that window, you're either trading accuracy in frequency over accuracy in time. And actually our approach doesn't have that. So if we look at the next slide, what we see here is a spectrogram of a particular sample, and this is a combination of musical instrument plus voice. And this is for a window size is about 1024. Now, if you look here, you can see these bands, and these are the bands which actually indicate that you are making compromises of specific frequency groups where you actually get the same results. If you then look over the time perspective, which is the x-axis, you can also see that you're actually averaging, because this looks like a blurred image. Now we can increase the window size, which leads to a larger blurring effect, and so we can see that this is actually not as ideal as we wanted. If we then move to constant Q transform, which actually starts to change the window size depending on the frequency areas you're in, you can see that especially at the bottom, meaning the lower frequencies, we now have less of these blocks that are blurred, and it gets kind of more smoothed out over time, and we start to get higher kind of pitched, pixelated information at the very top. Now our approach then moves on and demonstrates that we actually can get some of that pixelation across all of the frequencies. Now, one of the disadvantages that we're currently working on is the fact that you can see a lot of vertical lines on this, and this is because our technology is still focusing on one of the elements, at least this particular type of spectrogram, but we've already been working on that, and that is evolving as we move forward. So if we now think about some of the applications, we are looking at how we can use this because we can now do better decomposition of audio. We should be able to construct better cochlear implants. We should be able to also produce higher quality music compression instruments, and these are some of the things that we are exploring at the moment. So from a cochlear implant perspective, what normally happens is the audio is decomposed, then it is turned into a spiked pattern that is being fed into the brain. What I've got now is a few short demos of what the difference is in quality by using our approach versus what is the current approaches when used for audio decomposition. And so I've got two sets of samples for which I'll play the original, which hasn't been mingled with. Then I will play the current approach where you do the audio decomposition and then you go back and reconstruct it using a similar approach. And then our approach is again done the same. We have decomposed it and reconstructed it. And you will hear very quickly that there is a substantial difference between the two. The first one is a violin sample and the second one is a voiced sample. And so here we go for the original violin sample. So if we now go to the current approach, don't be surprised, this is not very good. So you can hopefully appreciate that it's really hard to understand the original from this current approach. And this is also why a lot of people with cochlear implants now need so much training time, because they need to filter out a lot of that noise. Now moving on to our approach. And so you can recognize that original coming back very quickly. If we look at an audio sample as into a voice sample, because of the frequency difference in what's happening, you're going to hear in the current one something that kind of resembles this to some extent. So your noise is going to be slightly different, but focus on, what you heard in the original and you will see some of that coming through. And then again, moving to our approach.
All of my life for you.
Right, so these are the demo samples, which then brings me to the end of the presentation. And it really gives, I want to have a very quick overview of what we've seen, what we've covered. Conventional computing is not really ideal for AI. We are using it as a test platform, which is great. But there is a need to move on and try and do better. And that not only comes from the big data challenges, but from a large set of other applications, autonomous driving, etc., where we can benefit from these technologies. It will require us to approach things differently, and it will probably lead to some very interesting applications, as we have discovered already along our journey. So that brings me to the very end. Thank you very much for sticking with me so far. I hope you enjoyed this presentation and the research seminar as such, at least this presentation in the series. And so if there's any questions with regards to the talk, please feel free to join me on Teams or drop me a line and ask your questions. Thank you. Bye.